Hey guys, welcome into the Wells Tech Garage for this month's training class. Today we are going to be talking about the wideband oxygen sensor, or the air-fuel ratio sensor, whatever you might want to call it. That's what we're going to talk about today. Now this class is going to be kind of a continuation, or let's call it a sequel, from our last class on oxygen sensors. So if you haven't checked that out, I definitely recommend going back and taking a peek at that, because a lot of the information that applies to a narrowband standard oxygen sensor actually corresponds directly to a wideband or air-fuel ratio sensor. Things like installation tips, do's and don'ts, things that contaminate or kill sensors, that kind of thing, they all apply also to a wideband sensor. So to save time, I'm not going to get into any of that today. I'm just going to cover the operation of a wideband sensor, how they function in a vehicle, and we're going to do some testing on some vehicles. Now, guys, I wish I could stand here and tell you everything that you're ever going to need to know about wideband oxygen sensors, but honestly, unless we're only talking about a specific vehicle manufacturer, it's nearly impossible to do, because like everything on cars nowadays, everybody's completely different. I can't teach you guys the system of wideband sensors without getting specific to individual vehicles. So I have some examples. I have two vehicles in the shop. I'm going to show you guys as much information as I can to get you going in the right direction. But research and verification and looking at your code data, looking at your trouble code setting criteria, that's all going to be very important to do when we're talking about widebands, because again, they can be very, very different on different vehicles. Now, before we get into how they work and what they do, let's give away some t-shirts. So for those of you, again, who aren't familiar with this, every class we give away a t-shirt if you answer our t-shirt giveaway question correctly. So the question today is, a wideband oxygen sensor set a heater circuit trouble code, and the heater has been diagnosed and it has failed. It's not functioning whatsoever. Technician A says, this doesn't affect the sensor's operation really, it just takes longer for the sensor to heat up by using that hot exhaust gas, and it'll eventually start functioning. Technician B says the sensor will not function at all without the heater and it needs to be replaced. So who's correct? Technician A, Technician B, C for both, D for neither. Go ahead, chat in your answer in the little text box here. If you guys are watching on our website, you do have to be signed into your YouTube account in order to be able to chat in. Otherwise, if you're already on YouTube watching, you should be able to chat in there. So go ahead, chat in that answer. This is only really intended for our live audience. And if you guys are having issues, shoot me out an email. I'll bring that up later in the broadcast and let me know what's going on. So I'll get to this in a little bit. Once we get over to the vehicles, we'll give out the answer. But honestly, guys, if you pay attention in this part, chances are you'll be able to get the answer correct by the end of the broadcast. Okay. Fuel trims number 3, the wideband oxygen sensor. First of all, the sensor has a ton of different names. Wideband, air fuel, AF, LAF for lean air fuel, UEGO for universal exhaust gas oxygen sensor, linear, AFR, I'm probably forgetting some here, guys, but the point of this is almost every manufacturer has a different name for the same sensor. It is a sensor that sits in the exhaust manifold and tells the computer what the air-fuel ratio is. Now, the point of a wideband is, I guess exactly as it sounds, it covers a wider band of air-fuel ratio. Remember, our narrowband sensor was only accurate at that 14.7 to 1 mark. Our wideband sensor will see accuracy down to like the 12.1 to 19.1, 12.1 on the rich side and 19.1 on the lean side. Now, there are some sensors and some vehicle manufacturers out there who are dipping that rich side lower and that lean side higher. But as a general idea, we're monitoring in between that threshold. So the major benefit of a wideband oxygen sensor or air-fuel ratio sensor is that it's able to look at that air-fuel ratio imbalance, any sort of issues, and it's able to almost instantly correct what's going on with that. Instead of our narrowband sensor, which are switching, and then we see our short terms start to ratchet down, on a wideband sensor system, you'll see those short terms react almost instantly right to where they need to be to bring that mixture back to lambda or stoichiometric or 14.7 to 1, whatever it may be on your scan tool. Okay, so that's the basics of a wideband. So why do we use widebands? Well, with increasing technology and increasing emissions standards, we need to have a faster, more accurate way to measure our air-fuel ratio. In comes widebands, and they can react to changes in the air-fuel ratio around 100 milliseconds or 10 times per second. We might be able to see that reaction of the sensor reacting to air-fuel ratio. Now, I'm sure there's some sensors out there now on even newer vehicles that are reacting even faster. This might be an old, out-of-date number. The major, biggest, hugest benefit, most huge, benefit is instead of the narrowband sensor having to switch back and forth and the computer ratcheting those fuel trims, the sensor is able to immediately do it and know exactly how rich and lean it is. So it's not guessing that it's just lean somewhere above 14.7 to 1. No, it knows exactly that it could be 18.1 to 1 or 17.7 to 1 or something like that. It's able to know precisely where that air-fuel ratio is at that exact moment. So by controlling this accurately and quickly, we're able to decrease our overall vehicle emissions. Here is a data graph right off the scan tool of a pair of air-fuel ratio sensors on a, I believe this was our 2003 Lexus that we have in the shop. Now you can see we have some differences here, right? We're looking at AFS voltage, bank 1 sensor 1 and bank 2 sensor 1. And they look completely different than a narrowband sensor, and this is normal. This is not going to look like what you guys are expecting to see when you're looking for oxygen sensors. Air-fuel ratio or wideband sensors are typically going to be a flat line or much more flat than a switching constant back and forth sensor. Okay? So this would be a normal operating air-fuel ratio sensor PIDs on our 2003 Lexus that we have in the shop. Okay? So I wanted to show you guys that. Now here is some PIDs off of a 2013 Honda Pilot. So as you guys can already tell, we got quite a few PIDs here. You know, maybe with a narrowband sensor we're used to 4 or 6 or maybe even 8 PIDs. Well, you can tell we got a lot more information being told to us by the scan tool, by the computer, about what is going on with these sensors on this vehicle. And now these are only the air-fuel ratio sensor PIDs. Now if I add in both of the post-CAT sensors, which are normal oxygen sensors on this vehicle, we would have even more PIDs. These are only referring to the air-fuel ratio sensor PIDs. And actually that brings up a good point. Air-fuel ratio sensors or wideband sensors are typically only going to be the pre-CAT. So the bank 1 sensor ones and the bank 2 sensor ones are typically the air-fuel ratio or wideband sensors. Typically the sensor 2s, so bank 1 sensor 2, bank 2 sensor 2, will typically be still a standard oxygen sensor, standard narrowband oxygen sensor. I don't know of any vehicles right now that are running 4 widebands on them, but it's possible. If you guys know of one that's using 4 widebands on it, let me know. I'd be curious to know what's out there. But like this 2013 Honda Pilot here is running 4 sensors in total, but it's only 2 widebands and 2 narrowbands on there. Okay, and that's pretty typical for the modern day vehicle. So the need to know about widebands. Well, first of all, they look very similar to a narrowband sensor. You know, you got a wire harness, a connector, and a sensor element that gets, you know, threaded right into the exhaust. Same story of a narrowband sensor. Don't mistakenly put the wrong sensor in. It's possible it might even plug into the connector, and this is still going to be the same size hole that it's going to thread into. So it's possible to accidentally install a narrowband sensor in a wideband sensor's hole. Just be careful, make sure you get the right parts, otherwise you could you could really create some issues. Our good friend Eric O from South Main Auto actually has a video on this where he's looking at air-fuel ratio sensor on a Honda where somebody did just that. They installed a switching narrowband oxygen sensor, and he had to have the fun of figuring that one out, because I believe in his video it wasn't setting any codes, so crazy. But don't accidentally put the wrong sensor in. All right, wideband sensor can be represented in many different ways in our service information and our scan tool data's information. we might see it represented as a milliamps PID, a voltage PID, an EQ or equivalence ratio PID, or a lambda PID, okay? We're gonna see different ways for these sensors to be represented. This is key right here. There's no general rule of thumb for widebands. Again, every manufacturer is kind of doing things differently with their voltages, their inputs, their grounds. They're all kind of doing it different. So we can't just throw a rule of thumb at it and say, on the signal wire you should see 2.5 volts. I can't say that because that might only be equivalent or might only apply to one manufacturer. So every vehicle manufacturer is going to be a case-by-case diagnosis, guys. You have to do your research, and trouble code data is going to be key for this. You get your code, look at that code set criteria, look at that data, see if you have some values in there that the computer's testing for, then you can look for the same thing. You know, duplicate the problem. All right, a scan tool is necessary to diagnose most wideband sensors issues. Completely true. Wideband sensors are going to be very, very, very hard to diagnose not using a scan tool. And I'll get into that in just a couple slides here of why that is. And then on your scan tool, a lambda or EQ or equivalence ratio PID on an engine using wideband sensors is typically representing a real-time air-fuel ratio. That same PID on a narrowband sensor motor is going to typically represent the commanded air-fuel ratio. So keep that in mind. Lambda or EQ on wideband is real-time air-fuel. Lambda on a narrowband engine is typically commanded. Wideband heaters. So just like a standard normal load narrowband sensor, the widebands also have a heater built in, but heaters are absolutely 100% critical to sensor operation on a wideband sensor. A faulty heater is a faulty sensor, period, end of story. The heater fails, sensor's not going to operate. Not like a narrowband where it just might take longer to become responsive, it's not going to work. Temperature on these things is much, much greater. We're talking 13 to 1500 degrees Fahrenheit. And changes in that temperature affect the output values of the sensor. So the computer monitors, the PCM monitors the temperature of the sensor and maintains a specific temperature, a specific temperature of what it wants to see. And that way the signal coming out of the sensor is accurate. So that temperature can affect that. Computer's going to maintain that. Typically we'll see a 12 volt power source in, constant, probably from a fuse, and then the computer will pulse width modulate the ground side. Typically a cold sensor, you're going to have a higher pulse width to get that sensor up to temp, and then you'll see that scale back as the sensor gets hot. PCM then just tries to maintain that, let's say 1500 degrees, okay? So heaters, absolutely critical and much hotter. If the heaters failed, sensors failed. Okay, different widebands. Now, like I talked about, each manufacturer kind of has their own deal. Well, they kind of have their own deal with two different styles of sensors. So let's say, let's just call it this. We have two different styles of sensors, and manufacturers use one style or the other, or the best way is to do your research. But let's talk about those two different styles. So first of all, you have your single cell wideband. This is typically going to be 4 wires. So this is one of those circumstances where you could accidentally swap in a narrowband sensor for a wideband if you're not paying attention. So 4 wires, 2 typically for that pulse width modulated heater circuit, so our 12 volts in, our pulse width ground, and then 2 for the signal circuit back to the PCM. Scan tool data, again, is going to be super important. And again, you need to know if you're using generic data or enhanced scan tool data. Now, a lot of our full function, high-end scan tools are going to give us some enhanced data, but I just want to bring this up. Many of the OE diagnostic procedures that you look into for wideband sensors say they require the factory scan tool. And the reason why that is because of a little thing that happened back in the 90s with Toyota. So scan tool data on a Toyota from the 90s used to look like this. On a 4-wire sensor, you would see your voltage reading here, 0.5, 0.6, 0.66, 0.7, 0.8. You would see a value like that. Now, if you were to graph that out, it would remain pretty steady because it's an air-fuel ratio or wideband sensor, right? But say you didn't know exactly what you were looking at, okay? Say you were maybe didn't know that your 99 whatever Toyota car had a wideband sensor in it. You throw a scan tool on it, and you see it sitting steady at 0.66 volts, okay? Well, you have an air-fuel ratio, or you have a code in there for an air-fuel ratio or wideband sensor, and you're looking at this thing, and it's just remaining steady. But what you don't realize is that is actually perfect. I mean, 14.7 to 1. That engine's running perfect. But, you know, you want to be proactive. So you're going to go out there and you're going to try and change the way this thing is running to see if your sensor moves, right? So you take a vacuum hose off, create a vacuum leak. Narrowband sensor, you should see that voltage drop, right, down to that 0.1, 0.2 mark. Well, if you do that with this sensor, you're going to see a 0.8 volt mark at 18.5 to 1. So as we go lean, our voltage actually goes up, which is completely the opposite of what we're used to with narrowband sensors. And this is where the confusion came in by people trying to manipulate the sensor to make it react to something and it doing the opposite. So at this point, does it need a sensor? Are you throwing a computer at it, maybe some wiring, something like that? You don't know without knowing the enhanced data. So this data was kind of confusing. You know, 0.5 volts. If you run this engine rich, you would expect to see 800, 900 millivolts. Well, you run this engine rich, you're going to see 0.5 volts. So what happened then is we were granted enhanced scan tool data. So if you put the Toyota scan tool on this, if you put a full function tool on it, you're going to see completely different values. So instead of 0.66 volts, you're going to see 3.3 volts. Well, right away, that's telling me that I don't have a narrowband sensor in there, right? I already know that I have 3.3. That's not normal. It's not 0 to 1. So I'm not thinking the same way that I would be thinking if this was a narrowband, okay? And then I run it rich or lean, and it's going to respond accordingly. So the reason why this generic scan tool data is in here is because back in the early days of OBD2, it was mandated that your O2 sensor PID information was between 0 and 1 volt, okay? So when Toyota and Honda, which were the early adapters of air-fuel ratio or wideband sensors, when they decided to put these on their vehicles, they had to conform to this mandate, right? So their sensor wants to operate between 2.5 and 4 volts to read your 12.5 to 1 to your 18.5 to 1. So what they did is they just took their enhanced data here and divided by 5. So that's where you get 0.5 volts for 2.5 and 0.8 volts for 4. So it gets confusing. Eventually, the OBD2 mandate was kind of lifted or amended so that the enhanced data could be shown in there. The voltage differences could be shown, but just keep an eye on that. Depending on what scan tool you use, generic data like this can kind of screw you up, so be careful. Okay. Here is a wonderful drawing of a 4-wire wideband sensor. Okay, this is something that I drew up. Again, we still have our zirconia element in the center. We have our reference air and we have our exhaust gas, right? Just like a narrowband sensor. We have some platinum electrodes surrounding our zirconia, and we have this diffusion layer here, okay? So the whole point of this sensor right here is to maintain this platinum electrode at stoichiometric, at 450 millivolts, all right? So there's going to be a difference between these two chambers right here, between the diffusion layer and our reference air. So there's going to be this difference. It's going to create voltage. We want that to be 450 millivolts, or, you know, perfect stoichiometric, 14.7 to 1, right? So what the computer is going to do is it's going to pump current in or out of these electrodes, and what that's going to do is it's going to create this chemical reaction, and it's going to move these ions across their zirconia element. It's going to move some oxygen, okay? So if we're reading rich exhaust, okay, we're reading a lack of oxygen inside of our exhaust, we are going to control this pumping circuit. We're going to add some current to it, and we're going to make these ions, these oxygen ions, travel across here to bring that back to a stoichiometric mixture, okay? The whole goal of this thing is to maintain 450 millivolts right here by pumping oxygen across that zirconia element to maintain that, and then the computer monitors that milliamp reading, positive or negative, and the level of it. So if it's 0.5 or 1 milliamp, something like that, that's going to directly relate to a rich or lean condition, okay? So by knowing positive or negative is going to be rich and lean, and the level of how high it is rich or lean is going to be by that milliamp reading, okay? So I'm going to demonstrate this on our Lexus once we get there. It'll make more sense once we get that far. Okay, here is a 2010 Lexus RX 350 that I have a wiring diagram from, and I just wanted to show you guys what it's going to look like on a diagram. You're going to have your HA2A. This is going to be our heater control circuit. That's going to be that pulse width ground. Then we have our battery positive, which is just our voltage in for the heater. And then we have A2 minus and A2 plus. A2 plus being 3.3 volts, A2 minus being 3 volts. Okay, so what exactly do we have here? We don't really know by just looking at this. We have to do our research to figure out what exactly it is we're looking at in this diagram. So upon research, looking at Toyota service information, it tells me that our air-fuel ratio sensor generates voltage that corresponds to the actual air-fuel ratio. Perfect. The sensor voltage is used to provide the ECM with feedback so that it can control air-fuel ratio. The ECM determines the deviation from stoichiometric air-fuel and regulates the fuel injection duration. If the sensor malfunctions, the ECM is unable to control air-fuel. So basically, sensor voltage is telling the computer how rich or lean, and it's going to control our pulse width of our injectors. Simple enough, right? But there's this asterisk right here. And what that says here is the air-fuel ratio sensor is a current output device. So what the heck? It says here, air-fuel ratio sensor generates voltage. And then it says here, the air-fuel ratio sensor is a current output element. Read your service information. This sensor is a current output element. Therefore, the current is converted into a voltage inside of the ECM. Okay, that's very important, inside the ECM. Measuring the voltage at the connectors of the air-fuel ratio sensor or connectors of the ECM will show a constant voltage result. Okay, let that sink in for a moment. They're telling us the computer is taking a milliamp reading, converting it to voltage inside of its own PCM, meaning we cannot hook up a voltmeter, we cannot hook up a lab scope and monitor the voltage on this thing. It's not going to tell us anything because there's a conversion happening inside the PCM. So if I were to take a scope and put it across these pins, sure, I would see 3.3 volts here, I would see 3.0 volts here, but I could run that thing rich or lean all day, and those voltages would never change. But what we'll see is we'll see a difference in our voltage reading on the scan tool. So that's confusing. The scan tool is going to tell us that we're maybe reading 2.9 volts at that exact rich or lean moment, but our lab scope's still going to only read 3 and 3.3. So I'm going to demonstrate that, guys. I'm going to show exactly how that happens on this Lexus because it is confusing and it's kind of frustrating that it tells us that its sensor generates voltage and then it tells us again that the sensor is a current output element. So keep that kind of stuff in mind when you're diagnosing these things, is they can be tricky. It can really throw you for a loop, okay? All right, then we got a Honda Civic here, kind of a similar setup. Our power wire in, our pulse width ground, our sensor input, and our sensor ground. So our sensor input ECM voltage, 2.2 volts. AFS minus is going to be sensor ground, 1.8 volts. So you're starting to notice some sort of voltage trend here. When it comes to the ground wires on these things, they're not going to be at 0 volts or chassis ground. We have to pick these sensors up off of that ground mark and give them a floating ground or a reference ground or a computer ground or a sensor ground or whatever they want to call it. It's going to be off of 0. So Honda on this 08 Civic Hybrid is going to run sensor ground at 1.8. Lexus on this 2010 RX 350 is going to run sensor ground at 3 volts, okay? We have to pick that up off of chassis ground to take any sort of interference out of these things. They are very, very sensitive, so that's why they're not on chassis ground. So if you're testing and you're getting weird readings, remember you need to be using the sensors ground, not chassis ground, okay? Here's some Honda service information. I wanted to bring this up as a little laugh because they didn't really tell me anything that I didn't already know. They show an element with some heater terminals and sensor terminals, and they say the air-fuel ratio sensor operates over a wide air-fuel range. Sensors installed upstream of the converter and send signals to the ECM PCM, which varies the duration of the fuel injection accordingly. Doesn't really tell me anything, unfortunately. So again, on something like this, guys, you're going to have to look at your trouble code set criteria. You're going to have to look into that kind of stuff and see if you can find some of that information out there, okay? So 4-wire wideband rules. Well, first of all, there is no rules. There's no, nothing that I can just tell you guys every 4-wire wideband is going to operate this way, right? You need to treat every manufacturer, every vehicle, every sensor as a new diagnostics. 0% or 0 milliamp current flow is ideal. That is going to be your stoichiometric or lambda mark. So zero current flow on, I believe, all of the 4-wire widebands will be stoichiometric. The sensor has to be hot. If the sensor's not functioning, if the heater's not functioning, the sensor doesn't function. Current positive or negative could mean rich or lean, so this could really throw you off. You're looking at your scan tool, you see your milliamps reading. On a Toyota, positive milliamps means the engine's running lean. On a Honda, positive milliamps means the engine's running rich, okay? So keep that in mind. We need to know what we're looking at, okay? Remember, you can always trust lambda. Lambda's not going to lie to you, so if you're showing a 1.2 on lambda, it means the engine's running lean. If you're showing a 0.8 on lambda, it means the engine's running rich, okay? And then you can watch how the wideband reacts with that. So that might give you an idea of how that wideband's reacting. Okay, fun fact, Honda's ULEV, or ultra low emissions vehicle, 2.3 liter back in 2001, was able to support fuel trimming for individual cylinders with 4-wire wideband sensor and a special exhaust manifold design. So we talked about that last class a little bit about how nice it would be to be able to trim each cylinder individually, because sometimes you have a single cylinder deviation that you want to correct for. While on most vehicles you have to correct the entire bank. Well, that can take a problem that maybe wasn't that bad and make it worse. Back in 01 already, Honda was able to do this and trim each cylinder individually. So cool little fun fact. Okay, our dual cell or pumping cell wideband. Now this is probably going to be more common today. We'll see this on most of our newer vehicles. That's typically going to be a 5-wire sensor. I got 5 wires right here. An external air source is not always going to be required. So for you guys that are into, off-roading or whatever, where you could possibly contaminate your sensor, these are not going to require an external air source on all of them. That's not the case for everything, but I know for example, a Ford does not require an external air source. Again, it needs to be hot. Always look at your wiring diagrams, etc., service information to get exactly what you need to know about that sensor. Again, reference low or ground reference is not chassis ground, and a scan tool may use milliamps voltage or lambda to represent the signal for the wideband sensor. Here is a cool little drawing, I guess, of a 5-wire or dual pumping cell wideband that I drew up, okay? So we have our PCM over here, we have our sensor over here, and the connector for the sensor over here, which is very, very important on these sensors, okay? So let's start with our heater element. We have battery positive in, goes across our heater, goes to a pulse width ground from the computer, maintaining our sensor around that 1500 degree mark, okay? Then we have a pump cell, measurement chamber, a nerd cell, and a reference oxygen chamber, okay? So exhaust flows into our measurement chamber. Just like on a narrowband sensor, we have exhaust flowing in, okay? And there's going to be this voltage differential across our O2 sensor, right? On a narrowband. Well, that's what this is right here. Our nursed cell inside of here is essentially a narrowband sensor, right? So the whole goal here is for the computer to maintain this at 450 millivolts, okay? So the computer is going to do everything that it can to keep this oxygen sensor, narrowband sensor inside of here at 450 millivolts. So how does it do it? It sends current flow down our pumping milliamp wire here, positive or negative current flow into our pump cell. That cell then, just like on a 4-wire, will transfer oxygen ions in and out of our measurement chamber to maintain that 14.7 to 1 mixture in there. The computer will then monitor how much current it's sending, positive or negative, and that'll determine exactly how rich or how lean the engine is, whether it be an 18 to 1 mixture or a 12 to 1 mixture, okay? So 5-wire sensor, 450 millivolts, it's trying to maintain that, pumping current back and forth. Now, the reason why a connector is super important on these sensors is most of them have this thing called a trim resistor right here. This resistor is built into the connector, and it's in there to accommodate for discrepancies in manufacturing, okay? So there's going to be a trim resistor in there, and almost all of these connectors have them. And that is also the reason why you'll typically see 6 wires going into the sensor and only 5 coming out. So 6 wires from the PCM, 5 coming out, right? And I can show you that here. We have 1, 2, 3, 4, 5 wires out, 6 wires in. Well, one of those pins, this pin right here, is tied to our current trimming resistor, and this is pin 2 right here going out to the sensor, okay? So this is why we have 5-wire sensors with 6 wires going to them. It's not going to be that you got the wrong sensor or something like that. Somebody didn't chop a wire off of it. That is common to happen, and that's just to make up for manufacturing discrepancies, okay? So common to happen. Not all PCMs will have that 6-wire going to it. Some do, some don't, okay? Here's some examples. Here is a 2013 Taurus, which we have in the shop right over here. We're going to do some testing with. You can see all 6 wires are here. 1, 2, 3, 4, 5, and 6 going to our sensor. So they're monitoring the current trim resistor, okay? And you can see we have all our pins laid out here. I wanted to really talk about our ground reference. It's actually 2.4 to 2.6 volts on this sensor. So again, not chassis ground, not 0 volts, not our normal ground. 2.4 to 2.6 is normal on a 2013 Taurus, okay? Then we have our 2010 Accord 3.5 here, and we have 1, 2, 4, 5, and 6. So we're skipping wire 3, and that's because the computer isn't monitoring the trim resistor on this vehicle, okay? So sometimes you'll see 5 wires, sometimes you'll see 6. Again, look at your service information, please, please, please. Figure out what you have in front of you on the vehicle that you're diagnosing, okay? So Ford was very, very nice in giving us a lot of information about their universal heated oxygen sensor. Now, you hear universal and you think, okay, well that's kind of weird. Is this one that I got to wire up? No, it's not the case. That's just what Ford calls it. They also call it a UEGO sensor. And I'm just going to read off some of this. I'm not going to read the whole thing. But I want to talk about this because Ford really shared a lot with us. It says that it uses a typical O2 sensor combined with a current controller in the PCM to infer air-fuel ratio relative to stoichiometric. This is accomplished by balancing the amount of oxygen ions pumped in or out of the measurement chamber within the sensor. The typical HO2S within the universal HO2S detects oxygen content of the exhaust gas in the measurement chamber. The oxygen content inside the measurement chamber is maintained as stoichiometric air-fuel by pumping oxygen ions in and out. As the exhaust gas gets richer or leaner, the amount of oxygen pumped in or out changes, and that is what gives us our air-fuel ratio. The measured air-fuel ratio is actually an output from the current controller in the PCM and not a signal that comes directly from the sensor. So just like on our 4-wire on our Lexus there, you can't just throw some test equipment on here. You've got to look at your data information. So just like I talked about in our graph here, we have our standard oxygen sensor, our nurse cell, trying to maintain that stoichiometric 450 millivolts. So we're going to pump oxygen in and out of our measurement chamber, and that's going to change our current flow right here, positive or negative, and then our level of current flow, whether it be 0.5 milliamp, 1 milliamp, 2 milliamps, whatever it is, will have a direct relation to the air-fuel ratio, okay? It also says here this universal HO2S does not need access to outside air. It will actually pump small amounts of oxygen ions from the measurement chamber into the reference chamber, okay? So no needed reference air coming in from the outside. And again, part-to-part variance is compensated for by placing a resistor in the connector. The resistor trims the current measured by the current controller in the PCM. So Ford connectors will have that current trimming resistor inside of them. Last line here, the O2 sensor is embedded with a heater that allows quicker closed-loop activation as well as maintaining the temperature that it needs to be at, okay? Another cool thing that Ford did is kind of like Honda did back in 01. They have an air-fuel ratio imbalance monitor that estimates the difference between cylinder and cylinder using the front universal heated oxygen sensors on both banks. It's going to look at a bunch of engine revolutions and figure out a signal of the pulses going past that sensor from bank to bank, and it's able to notice deviations in each cylinder and trim each cylinder accordingly. So kind of cool that Ford's doing it now as well. And then this bottom little box down here, guys, is just something I pulled out of the service information. that is for the ground reference or ground voltage level of that ground. So you'll see here our 2.0 Taurus is going to read that 2.4 to 2.6 volts on the ground reference wire, okay? Here we have our 2010 Accord again up on the screen. I just wanted to call out what some of the pins did. So you can see all these pin values. Now, it didn't tell us anything here. We have sensor input, sensor input. Where I found this information was actually going through the PID information out on the service info. You can find a graph sometimes that looks like this. Pin number 14 right here says with engine warmed up and running, 3.4 to 4.8 volts. So pin 14 right here, sensor input, 3.4 to 4.8 volts. When I tested it, I was reading 4.05. Our reference voltage on here, so our ground voltage is going to be 3.4 to 4.8 also. I tested it at 3.5. Our sensor input is 2 to 5.6 volts. I tested it with a varying 3 to 4 volts. So that moved with differences in the air-fuel ratio, okay? Now what I think is interesting here is if you do the math between our, let's call it our signal and our ground, right here between these two pins, between 4.05 and 3.5, what does that come out to? 450 millivolts, right? So the computer's watching this right here for that 450 millivolts, and it's changing the current on this wire right here to pump those oxygen ions in and out to maintain that 450 millivolts, okay? So that's a 2010 Honda. So wideband sensors and fuel trims, okay? So that was how a single cell and a dual cell sensor operate. Make sure you do your homework, make sure you do your research on the vehicle that you're working on, but that's basics of how those sensors function. Now let's talk about how they function with our fuel trims. So wideband sensor, you might not see your percentage values anymore. You know, we talked about like that plus or minus 10% to set a code type of thing. You might not be able to see that anymore. Your research will typically reveal what you're supposed to see on the scan tool. And you can look into code set criteria for like a lean code or a rich code. That's typically where you can find that information. So let's take a peek at some data that I captured here. So we have on top our long-term fuel trim and on the bottom our short-term fuel trim. And you can see that our numbers are just completely different than what we're used to seeing. Long-term current is at 0.93 with a max and a min of 0.93 and 0.92. Our short-term fuel trim is currently where our cursor is here at a 1.47, but we saw a swing between the minimum of 0.69 and the maximum of 1.47. And you can see a bunch of changes in here. I was actually manipulating the air-fuel ratio on this engine. Here we add in two more graphs. We can watch the air-fuel ratio lambda, or our air-fuel lambda right here, increasing, plus and minus of 1. And we can look at the milliamps on our sensor, so our pumping current, how all this works, okay? So our lambda right here where our cursor is was reading at a 1.7 lambda mark, okay? So what does lambda 1.7 mean? That means we're running lean, right? Lambda is high, above 1, we're running lean. What does our air fuel sensor milliamps do? It goes negative on our current, negative 0.43 milliamps on our current. And what does our short-term fuel trims do? They spike up, 1.47, and they stay there until the vacuum problem is corrected, okay? And you can see that by the demonstration of the map sensor here with our voltage. You can see our voltage spike up when I pull the vacuum hose off. And you can also see our air-fuel ratio PID right here spike up as well. Where our cursor is sitting, we're at a 25.1 to 1 air-fuel ratio. So this is telling me our short-term fuel trims are reading a 1.47 at a very, very lean mixture. So what does that mean? Again, did some research. Honda service information says, and I'm not going to read this whole thing. If you guys want to read it, go ahead. But I'm just going to read this part right down here. When long-term fuel trim is higher than normal, which is about 1 or 0%, the amount of injected fuel must be increased. Well, obviously, that's the way that our fuel trims work, right? And when lower than normal, it must be decreased. If long-term fuel trim is higher than normal, it's too lean. Now, that normal malfunction threshold, long-term fuel trim is higher than 1.25 or 25%, okay? So we're adding 25% on our short term if we're reading a 1.25. So if we go back here, we were currently reading a 1.47, so let's call that 47% then, right? So 47% positive short term means we're running incredibly lean and we want to add in more fuel. So it's still reacting the same exact way that we're used to, the numbers just look different. And rich is going to be the same way. When it's lower than normal, it must be decreased. If long-term fuel trim is lower than normal, it's reading too rich. Our malfunction threshold here, long-term fuel trim is lower than 0.8 or 20%. Now, I thought this was kind of interesting. The thresholds are different, rich to lean. This engine is more sensitive to rich concerns than it is lean. So it's allowing a positive, let's call it a positive 24%, won't set a code, but a negative 20% or negative 24% will set a code for rich, okay? So if we look at our, let's go back to this one. Currently we're reading 1.47, so let's call it 47% lean, okay? When we're reading this 0.69, that doesn't mean we're running 69% lean, okay? Don't get confused here. We're starting at 1, not at 0. So we have to subtract from 1. So that would actually be roughly 31% lean or so, okay? Excuse me, 31% rich, okay? We're subtracting 31% fuel, okay? So start at that 1 mark. When it goes below that, we are taking fuel away. When it goes above that, we're adding fuel on our fuel trims, okay? So some closing thoughts on our wideband sensors. Again, I can't really give you guys a lot of rule of thumbs here or system operation because every vehicle is so different. You're not always going to find the information that you need to diagnose these things. Like we saw with that Honda sensor, we didn't have a ton of information on it. So what do you do if you don't have the information you need? Well, there are going to be a few things that you can do. First of all, verify your heater's operating. Remember, if your heater doesn't function, the sensor doesn't function. Throw an amp clamp on it and check if it's operating, right? See if it's pulling amperage. It should look like a square wave because the computer's pulsing it, okay? You could potentially swap bank 1 and bank 2 sensors, okay? If it's a 2-sensor engine, swap them over, see what happens, see if the code travels. Pull out the sensor and look for contamination or damage to the sensor, just like a normal O2. They can be contaminated, coolant, oil, all that fun stuff. And these things do wear out. They're still in the exhaust stream. They're still not going to last the life of the vehicle. And then last but not least, we have to trust our computer, okay? Wideband sensors will fail, and when they fail, the computer has way more tests and way more codes for a wideband sensor than they do a narrowband sensor, okay? So chances are if you're getting a code for it, it's probably for a reason. I wouldn't say throw a sensor in it, but let's look at some data, let's look at some PIDs, and try and figure out what's going on with this thing, but we do need to trust our computers, okay? So with that being said, our next class is going to be fuel trims number 4. We are going to finally after months here, we're finally going to fix the GTO, show you guys some tips and tricks and processes for figuring out rich and lean conditions and that kind of thing. So that's going to be next month in April. But for now, I think it's time to head over to our Lexus and our Taurus and hook up scan tool, scope, amp clamp, and demonstrate some of these processes and tests that we showed right here. We're going to manipulate some sensors and see what happens, okay? So Fritz should have everything hooked up over there, so I'm going to head on over and let's see what we got. All right.
Hey, Mike.
So we're all set up here?
Yeah, we're all set up. All set up, ready to go.
Okay, good to see you're not sleeping.
Well, no, that was good information. I bet you got a lot of these guys with their head spinning.
Well, hopefully not too much. Hopefully by demonstrating some of this stuff, we'll be able to really bring it all home.
Yep.
Hopefully you guys are still awake out there. Sorry that it was so long-winded again, but I had a lot I wanted to talk about, I guess. Mm-hmm. And now we have a lot that I want to show you, so sure. Let's go ahead and do it. Why don't we first bring up some engine data from our 2003 Lexus RX 300 3-liter V6 in here. So let's bring up some engine data. If you want to go ahead and fire this thing up, Fritz.
Sure.
We can take a peek. I'm just going to go into our air fuel O2 sensor data screen here on our scanner. And let's just see what we got. So Snap-on's been nice enough to pre-select us a whole bunch of PIDs here. I don't really care too much about all of it. I wanna zoom in on some stuff here, and let's bring up a custom graph. And let's just grab a couple. Now I have the lab scope hooked up on bank 2, so I'm just gonna grab all the stuff for bank 2. So I'm gonna grab short term, long term. For bank 2, let's grab, not that one. Let's grab this one here, bank 2 sensor percentage, bank 2 sensor voltage. Let's grab AF2 test, and don't need any of those. I think that looks good. What do you think, Fritz?
I think that'll do her.
That's enough? All right, so here is the PIDs for this vehicle. Our fuel trims are still in a percentage, so we're at 3%, and actually it's 2.31 or 3.09%. Long terms in a percentage, and then our voltage here, just like I was talking about with Toyota vehicles, our voltage is changing. And it looks like our test is complete. I'm gonna go ahead and throw these up in a graph so that we can see what they look like in a graph over time. And we're watching our voltage here. This is our sensor reacting to different conditions. You know, the engine's not going to always run perfectly, so this is just the sensor reacting. It's not actually switching. We're not switching between that 900 millivolts to 100 millivolts. We're only between 3.2 and 3.13 right now. So it's running very, very well. We're right around the 0 mark for our fuel trims. What do you think, Fritz? Should we see if we can mess it up a little bit and see if we can make this thing move?
Let's do it.
Let's tweak it and show how it reacts. And then we'll bring up the lab scope in just a second here. Go ahead and let's manipulate the sensor. What are you
Okay,
gonna
first
do?
thing we'll do is we're going to give it some air.
Okay, create a vacuum leak?
Yep, create a vacuum leak.
All right, and let's see how the scan tool reacts. Let's see how the voltage reacts. All right, so you can see right away where our voltage spiked up. Right there, it spiked up, and our short-term fuel trims reacted. Now, what I want to really draw out here, guys, is look at this line right here. You see that? That's how quickly this thing is reacting. Now go ahead and hook that hose back up, Fritz. And we should see our voltage now drop. There we go. And look how fast our short terms just reacted. We're talking almost instantaneously here, guys. These sensors are able to respond so quickly, and we don't have that ratcheting effect anymore with our short terms. That's not present anymore. No, we're not seeing that happen anymore. So now let's bring up the lab scope. I have the lab scope currently hooked up. We're running right here, and we're running at that 3 volt mark and that 3.3. If you remember in the diagram, let's zoom in so you guys can see it. Here's our diagram. We are on bank 2, so I have pins 1 and 3 hooked up on the scan tool right now. 1 and 4. No, sorry. 3 and 4. Let's see if I can get the right numbers here. AFL plus and AFL minus. Okay, 3 and 4 are hooked up. That is where we're reading our 3 volt mark and our 3.3. Okay, so why don't you go ahead and bring up our scan tool on the screen. There we go. And Fritz, go ahead and pull that vacuum hose again.
Yep.
So now again, guys, we should see this thing drop, right, on our sensor voltage right here. Or excuse me, it should increase with a vacuum leak. We saw it increase, we saw it react, we saw our short terms jump up. But we didn't see any changes right here, right? Nothing whatsoever. Okay, go ahead and let's give this thing some fuel once.
Okay.
And now we're gonna run it rich by adding in a little bit of fuel. And immediately we'll see our voltage start to drop. Go ahead and open it just a little further. There we go. So our short terms are reacting. Everything is reacting like it's supposed to our changes in fuel, but still, look at this. No changes whatsoever in this line right here. These are completely constant. Okay, go ahead and shut it off. And now the engine's gonna have accommodated for this extra fuel. And there's our spike again back to lean, just like it's supposed to. So we know at this point that our sensor's functioning perfectly fine. It's able to respond rich, it's able to respond lean, it's working fine. So you could do this kind of thing when you're questioning a sensor, you could force the engine rich, force it lean, and see if it can respond. If it can respond like that one is, probably just fine, right?
Yep.
And then, okay, why don't you go ahead and hook that vacuum hose up, and we'll just see the vehicle react back to where it needs to be.
Almost
and
instantly.
Short terms drop, yeah, almost instantly. The one thing I did want to bring up here is look at our long-term fuel trim, guys. It's reacting a lot slower than our GTO did. Our GTO's long-term, when we were doing that in the last class, those long-terms adjusted pretty fast.
Pretty fast, yeah.
In all intents and purposes, it was I don't know, 10, 15 seconds, something like that. The long terms on here are taking quite a bit of time to react. So short terms, very, very fast. Long terms are taking a little bit of time. So, all right. Okay, so let's say that you aren't going to watch the voltage, but you want to make sure the heater works, right? So what we do now is I have channel 3 of the scope hooked up to the voltage side, the control side of the heater circuit. So I'm going to go ahead and throw this on 20 volts. And there's our heater. Let's go ahead and throw on a trigger. I'll put a trigger on channel C so I can grab our heater control. And you can see here we have, looks like we're running 14.4, so battery voltage when it's charging. And then the computer grounds the circuit, drops it down to 0, or very close to 0. We're reading under a volt, and then it brings it back up. So this is that pulse width on that heater control, okay? So the computer's pulsing it like it's supposed to, but we don't know if we're flowing current yet or not. So I'm gonna go ahead and turn on our 4th channel. I have an amp clamp on here. And let's put this on let's start at 1 amp and see where we're at. And we're spiking on that one. Let's go to the opposite end here. Okay, so now we're reading on a 10 amp scale. And I'm gonna go ahead and I'm gonna drag this down so we can see it. And there we go. So yellow is our amperage, green is our voltage. So this is pulse width from the computer, controlling our voltage. And this is the amperage flowing in the circuit. So we should expect these to be opposite of each other. When one is high, the other's low, right? So we're not grounding the circuit right here. Computer turns it on, grounds the circuit, allows for current flow. So our current's flowing right here, right? It's increasing. Then the computer turns it off, it goes back to battery voltage. Computer turns it on, we flow current again. So with this vehicle heated up, this sensor's reading roughly just over 6 amps of current travel to keep the sensor hot and operational, right? These sensors have to be hot to function. So it's up around that 6 amp mark on this vehicle. Now, this is kind of common for these older vehicles, right? I mean, 5, 6, 7 amps, something like that to keep these things hot. As sensor technology increased, on the planar design sensors, they actually will run a lot lower, 2, 3 amps, somewhere in there. We should be able to see that with our Taurus. We should see a lot less amperage on that. But okay, so we know that our sensor is able to function to rich and lean conditions, right, Fritz?
Yep.
If you want to head back over here, then they can see the front of you again. So we know that our sensor is able to function right back and forth, rich and lean,
Yep.
and we know our heater's working, so we're good to go, right?
That's right.
If you ever have questions on the operation of it, if it's working or not, you could always compare it to the other bank then as well. You know, in your data, if you're working on a V6 engine, look at the left and right banks, compare them together, and see what you got.
Right.
That might help out. Okay, ready to go over to the Taurus?
Yeah, let's do that.
All right. Now we do have to transfer over all of our lab scope stuff here, so it's going to take just a second to get this all transferred over. You can go ahead and shut her down. I'll get our connectors disconnected here. You got the scan tool?
Yep.
All right. And Dave, can you bring up that picture under the hood here? So this is what it looks like under the hood of this thing, how I have it all hooked up. You can see I got some blue connectors on here. I'll show you guys in just a second what exactly those are. So I'm going to just hook in. We'll start like this, and we'll tweak it from here because I'm going to show you guys a couple different things here. But we'll start like that. All right, we're hooked up to ground. And all right, we'll disconnect our amp clamp from the first one. Okay. So what I'm using for this vehicle is these cool little leads that came with the picoscope. It's a male end on one end and a female end on the other. And it's just nice for doing something like this because we have to, we can't break the circuit to test this thing, right? Because we have to keep our heater functioning in order to test our sensor. If the heater's not working, the sensor's not working. So I hooked these up in line, and I'm able to hook the lab scope up right to it. So these are a cool set of test probes. If you guys don't have anything like this, definitely check it out. You might even be able to find them out at like ASE Wave or something. But they're nice to have. I got a set of 6 in this pin diameter. I have the blue color there for a different pin diameter. I think there's like 4 or 5 different sets here for different pin diameters. So definitely check these things out. They're nice for testing while still keeping the circuit intact. All right. So Fritz, what should we look at first? Should we look at the data from this thing? All right. So let's exit out of here, enter in our vehicle. You got the key on?
Oh.
So we're working on a Ford, we're working on a 2013 Taurus, and this is the 2-liter turbo. And let's go to data and see what we have for, oh, no communication. You want to wiggle the connector around?
What's that? Nothing yet?
There it is. And let's find our fuel trim O2 sensor data. And then you can go ahead and fire this thing up, Fritz, and we can take a look at what we have for scan tool data on here and how it's reacting. So this is going to look a lot different than our Toyota. This Taurus is running that 5-wire sensor, which we talked about second. And you can see already we have a ton of information in here, right? So this just keeps going on and on and on. Look at all these PIDs. Look at that. So a lot of this is really, really good information, but I'm going to try and clean it up a little here by just creating another custom graph. And I'm only going to bring up things related to our Bank 1 sensor, sensor 1. So lambda, equivalence ratio, we bring up our milliamps. And don't be fooled by this exhaust gas oxygen sensor. You know, the first thing you see is exhaust gas. You might be thinking EGR, but this is that EGO sensor, or UEGO from Ford, okay? So that means that Bank 1 sensor 1 air fuel ratio or wideband sensor. Let's look at this. We'll bring that up. We can look at heater command, status, control. Let's throw some fuel trims in there. So as you guys can tell, as we're going through this, there's a lot of things related to Bank 1 sensor 1. And let's throw short terms. Okay, so now our list is a little bit smaller. And right away, this is what stands out to me, these two right here. Our equivalence ratio, so this is desired now. So this is telling us what the vehicle wants. It wants a 14 to 15 to 1 mixture right here. And our milliamps on our sensor. Okay, so we're talking 0.018 milliamps, so it's tiny. Really, really small amount of current flow here that the computer's monitoring. But that is what the computer is then relating back to change our fuel trims, okay? So you can see currently we're running about a 5.5% adding fuel, 6.3 there. So it looks like it's maybe running just a hair lean. We got sensor status, okay, impedance expressed as voltage is 1. No fault in our sensors, that's a nice PID. Gives us a no fault. We have some resistance PIDs here, warm and ready. So a lot of information that we can see. Okay, let's take a look at our lab scope now. Let's see what we have on here. So it's kind of a mess. I only have the first 3 channels hooked up right now. So what are we looking at? I'm on pin, and I'll bring up the diagram here. We are on pin 1, 2, and 3 right now is all that I have hooked up. I just went with those first. And I'll go ahead and zoom in. There we go. So currently pin 1, so we're looking at our pumping current. Pin 2 is our ground reference. And pin 3 is our heater circuit. Okay. That's the heater control, the ground side control for our heater. So let's see what we got. Alright, so it's a mess. Let's go ahead and zoom in on this because we're looking at this heater control is pretty fast. So maybe a little too far. Okay, so now we have our heater control, and it looks just like a square wave like we saw in our Lexus. Looks nice. Then we have this red line here. This is our ground reference line, and that is currently reading about 2.527 volts. So this is actually our ground reference, okay? This is that ground for the signal, okay? And then on channel 3 here, we have this pumping current that you can see is actually moving. And I'll zoom this out a hair so maybe we can see a little bit more of the motion in this thing, okay? Fritz, can you go ahead and pull that hose off of there? And we'll see this thing react a little bit to the change. But not much. Go ahead, Dave, can you bring up the scan tool on here? There we go. And I'm actually gonna, let's look at this. Okay. All right, so this is our current pumping right here. So we're watching it in amperage on the scan tool, and we are watching it in voltage on our scope. Okay, go ahead and hook that thing back up now, and we'll watch it respond back the other way, or it should. And there we saw a dip as the whole thing reacted, and the voltage here did something, it moved, right? But we don't really know what it's doing because we're so far in. So I'm gonna back this back out a little. We'll go down to 1 second, and you can see as it's coming across the scan tool, we're getting some increases and decreases in this, but this isn't what we're really looking at here. We don't really care about this signal, I guess, okay? Because just like it was for the Toyota, for the Honda, we want to be monitoring this right here. This is what we want to be checking when we're diagnosing that sensor. We want to be looking at that milliamp reading, okay? So when we're fixing these cars, we want to look at that. Fritz, you want to grab that propane and let's see if we can run this thing rich and lean and show how this one reacts. So I'm gonna take and I'm gonna zoom this back into that 20 millisecond mark.
Ready?
All right, go ahead. So he's gonna pull it off first. It's gonna run a little bit lean because we're creating a vacuum leak. And then he's gonna feed some fuel into it. You can give it a little bit more. And we'll see, there we go. So it just reacted there. And actually, if I bring this down, I'm gonna bring up our short terms. And so here's our short-term fuel trim. Here's our sensor. And then here's this. So this is right back to where it was before. Nothing's really changed. Now go ahead and shut it off. And we should see our short terms react and everything go back right to where it was supposed to. There it goes. So now we still have the hose off, so it's running slightly lean. The sensor's reacting. The short terms went up to where they're supposed to. And then now if you go ahead and hook that back up, we should see it come right back around that 0 mark. Sensor's right back around 0 milliamps, and we're coming back down. So this sensor reacts very similar to the way the Lexus did, right? Our Lexus showed us voltage on the computer. Our Ford is showing us current. But really, we just want to see changes when we're diagnosing these things. We want to see that fluctuation, that movement when you run it either rich or when you run it lean, okay? So let's do one more thing with this. Let's take a peek at that heater circuit again on this side. I want to show you guys something cool that Ford does. From the hook in our amp clamp, Go ahead, zero it out. And we'll hook up channel 1 to our heater. It should be that one, I believe. So what are we reading now? Okay, so our amp clamp is, looks like it's not reading right. So we got channel 3 for our heater circuit, and channel 4, let's go ahead and zoom in our amperage. Yeah, that doesn't look right.
This one right here.
Yeah.
That's the one.
Get it there.
Mm-hmm.
There it is. Okay. Now we got it right. So I'm going to go ahead, I'm just going to turn off these channels that we're not looking at right now. We'll turn that one off, and we'll turn that off. Alright. So let's see what we got here. So we're definitely spiking above the 1 amp reading, so I'm going to adjust this again. We'll go to 5 amps this time. There we go. Bring that down. Okay. So again, guys, I'm going to zoom in on here. We'll bring it down to this. Yeah, that looks pretty good. Maybe out just a hair. So you can see again, we're reading the opposite. So our voltage, you know, sitting right around battery voltage, 14 volts, drops down to about the 0 line. Oops. Turn that off. Drops to that 0 line, and we're very close to 0. Then it spikes back up. And then our amperage does the exact opposite. And if you notice here, guys, look, we're only at 1.6, 1.7 amps on this heater, so it's a lot different this time. It's not nearly as high as it was before with the other one where we were around that 6 amp mark. All right, Fritz, what I want you to do now is I want you to pull that connection apart for the heater circuit. So we're gonna pull power to this thing. So we should see our amperage drop out.
You ready?
Yep, go ahead. So our amperage dropped out, right? We're not feeding power to the circuit anymore, but look at this. See what that's doing right there? And now look. You guys see what I'm seeing here? So what could this be? What is happening right now? It's kind of crazy, but this is the computer, the PCM, actually hunting for the heater circuit, okay? So we saw this thing before. It was at 14 volts down to 0, 14 down to 0, 14 down to 0, in that beautiful square wave that we like to see. Now look what we got. We got a 3.6, 3.5 or so volt signal down to 0, 3.5 down to 0. What this thing is doing is it's looking for that heater circuit. It wants to turn that heater back on. But the circuit's not connected, so it doesn't want to supply that full amount of voltage, you know, up around that 14 volt mark, in case something shorted. It's kind of protecting itself here. So Fritz, go ahead and reconnect that, and we'll see. Actually, hang on. Before you reconnect that, let's bring up the scan tool on here as well. I'm going to move my signals up so they're out of the way of the scan tool. Uh-oh. There we go. And look. So proof here, we have no heater, we have no sensor operation, right? As soon as Fritz disconnected that heater right here, our sensor flatlined, our short term's flatlined, we have no activity. Now go ahead and plug that thing back in, and let's see if our heater comes back. And look at that. Almost instantly, the computer reacts, and you can see our pulse width changing. Oops, sorry guys, I'm moving the wrong one. And there we go, the pulse width is changing, the computer's happy again, and look at our sensor coming back on the scan tool. So sure, this thing's probably set a pending code already in the computer saying that the heater circuit went open. but the computer kept searching for it. Even though it had failed, the circuit had failed, it had gone open, the computer kept looking for it to try and correct the problem that it had and keep this thing going down the road. Now, if we, potentially, if we were to shut this thing off a couple times and get it to set a hard fault, it might actually, you know, not search for the signal anymore. I'm not sure. Didn't actually try that with a hard fault in there, where it actually set the trouble light or the check engine light on. But just when it's doing a pending code like this, it is going to keep searching for that signal. So I thought that was kind of interesting. I hope you guys think it's interesting. I thought it was kind of cool that it was going to keep looking for that signal. So,
Yep.
all right, you can go ahead and shut it off, Fritz. Actually, hang on one second. Sorry, I want to show one more thing here. I want to show this right here. So here's our ground reference, and that was at that 2.5 volt mark. And here's that UO2 S11. This is that nursed cell right here, okay? So remember, this thing's going to try and maintain 450 millivolts. So if I go ahead and hook in to pin 2 and pin 6, oops, sorry guys, I'm all over the place. I'm going to go ahead and I'm going to turn our scope on here and turn on channel 2. I'm going to turn these guys off, and let's hook into pin 2 and pin 6. So pin 6 is going to be our somewhere here.
There it is.
Alright, that is black for channel A, and channel B should be on red. Okay, let's see what we got. I'm going to bring these down so we get a nice even number here. So we're at 2 volts right here. Bring this one down so we're at 2 volts right there. Oops, wrong way. Okay, so we're running 2.5 and 3 volts. Okay, so if we do the math again on this, we're right at around that 450 millivolt mark. Now this blue line right here, which is connected to this signal right here, I'm using chassis ground for this, but watch what happens if I go ahead and take the ground for that one and change that over to the ground for red. So this should give us, look at that. So I just hooked it up, and where are we at now, guys? If I can click on it, and in fact I'll go ahead and I'll zoom this in to, hey, we can go to 500 millivolts. Maybe a little too far, the scope is getting some noise, but 450 millivolts. Now Fritz, go ahead and take that hose off again, that vacuum hose there, and we'll see on the scan tool, before it goes to sleep, we'll see it respond. We'll see our sensor respond in milliamps. There we go, she dropped. But our 450 millivolt line stayed perfectly straight. Go ahead and hook it back up, and we should see it respond again. And there it responded, and look at that, perfectly straight. So this computer is able to react so quickly that it's able to maintain that perfect 450 stoichiometric mark on that signal wire from that nurse cell. So super efficient sensors. All right, shut her down. Let's see if we have some comments from you guys. Holy cow, okay. We'll start at the top. Well, first of all, let's answer the question. So apparently a lot of you guys knew this one. Maybe it was too easy. Teke said that the heater didn't affect the sensor's operation. Well, we all know that that is completely wrong. We just proved it, mentioned it a bunch of times. Heaters are critical to our wideband sensor, right? No heater, no sensor function.
Sensor.
So Tech B was correct. So all you guys out there, Paul, Terry, Syed, Enrique, Shayla, Shedrin, sorry if I'm mispronouncing your names, Mohammed, Bob from Haywards, Richard, JJ. You guys all got it right. And oh, look here, Steve said it right also. So can you bring up my email on the screen? So you guys can go ahead and shoot me out an email with your t-shirt size and your mailing address, and don't forget the color of the shirt that you want, and I will make sure to get a shirt sent out to you as soon as possible. Let's see what else we got here for comments. Today I'm lucky to join your class. You canceled all the reservations and closed up the workshop to join me. So feel lucky. Mohammed, I do feel lucky. Thank you for joining us today. Looks like Terry had said something and then he took the message away. And Bob's answering that he had it correct the first time. Good afternoon. Oh, Tam Couch, good to hear you got your shirt all the way in Scotland. That's awesome. I'm glad you like it. Terry got the answers mixed up. Just answered this question on an ASE test. Awesome. So my ASE style questions that we make up, I guess, are similar to the ASE test. Cool. All right. Looks like Eric O is here. He says, dang, I'm really late. So good to see you here, Eric. All right, late lunch today for Eric, I guess. He's getting busy. The guys are talking back and forth. I guess somebody's having bologna sandwiches. So I'm not going to read through this whole thing. It looks like Drew joined us towards the end, is watching. Oh dear, the virus instead of the virus. Nice. Okay, graph view, yeah. Okay, use the Pico, yeah. Use generic, please. That's a good idea to use generic instead of vehicle specific. So yeah, you could definitely use generic data instead of specific vehicle data. Sometimes, as we all know, our vehicle specific data lies to us sometimes, right? The computer lies to us. So onboard Tech 333 has a good point that we should or could be using our generic data instead. So that way we get the best possible information from the generic side. And we got some more comments. Got to get back to work. So sorry, lunch is over. All right. 1500 PSI for fuel pressure. Yeah, this was a GDI motor, so it's common to be up around there. And another Tech B from Type E1. So again, could you just throw my email up again one more time? Put that up there. And okay. So I think that's most of them, guys. I'll read through them again, and if there were any questions in there that I missed, I'll address them during the next Tech Connect that's going to come out at the end of this month before our April class. April 6th is the next class, 11 a.m., 2 p.m. Central Time. We are finally going to be fixing up that GTO. So I think that's probably about it for me today. I talked a lot. Sorry for keeping you guys so late again, but I had a lot that, I mean, these things can be complicated, so I wanted to get it all out. Check out our social media, Facebook, Instagram, Twitter. Follow us out there. Like us on YouTube. Share the video if you'd like. Thumbs up. We like all that stuff from you guys. And all right, I think that's about it. So we'll see you guys again next time in the Wells Tech Garage. Thank you.